Here we are, PreCalc with 2.5 zeros. Okay, this is all stuff I believe that you've done before. So hopefully it's just a review. But, some of it might be new, or it might be a little further than we've gone before with it in the past. You know that an nth degree polynomial can have n real roots. In the complex number system, the statement can be improved. In the complex number system, every nth degree polynomial function will have precisely n roots. So if we're talking complex numbers, we can guarantee that it will have that number of roots as whatever the biggest power is in your function. So we can break those all down into linear factorization with all the roots. So let's get to it. A first degree polynomial f of x equals x minus 2 is going to have one root, or 1, 0, at x equals 2. 2 minus 2 would be 0. B, x squared minus 6x plus 9, that's x minus 3 squared, which would be x minus 3 times x minus 3. For the roots, x equals 3, x equals 3, or just 3 one time is a double root, or a repeated root. A repeated root, repeated 0, double root. All things that it's been called before for us. Okay, we got a third degree polynomial. X to the third plus 4x. We can pull an x out in front. Okay, and x squared plus 4, it's not a difference of squares, so that's tough to do. So that would mean it's going to have imaginary roots, and that's going to be x plus 2i, x minus 2i. If you want to go through and do that over here on the side, you could. X squared plus 4 equals 0, x squared equals negative 4, square root, square root. Square root of negative 4 is going to be plus or minus 2i. So we would have 0, negative 2i, positive 2i. More fun over here. X to the fourth minus 1. That is a difference of squares. That would be x squared plus 1, x squared minus 1. Okay, x squared plus 1, very similar to x squared plus 4. Sum of perfect squares means you're going to have imaginaries. And then x squared minus 1 is going to be just our normal difference of squares formula. So x squared plus 1 is going to be x plus I, x minus I. And again, if you want to prove that, you can go over here and do it on the side. X squared minus 1 is x plus 1, x minus 1. For our 4 roots of plus or minus I and plus or minus 1. So that was basically almost everything that we talked about in Algebra 2, all in one page. So, catch your breath a little bit. We've got the rational zero test. Long story short on this one is that you can take the last coefficient or term, divide it by your front coefficient, and that will be the list of possible rational zeros. Possible, not guaranteed that all of them are there, or that all of those numbers are going to be roots, and then rational, meaning answers that can be expressed as a fraction or relatively nice answers. You're not going to have your irrational or imaginaries. So, we've got 6 is our back number, and we've got 1 for the front number. So 1 can only be 1. 6 could be 1 times 6, 2 times 3. So our possible rational roots are all the factors of this back number divided by all the factors of the front number. Well, it's a 1 in the front, so that makes it really nice. And these are all plus minus. So we're looking for plus or minus 6, plus or minus 3, plus or minus 2, plus or minus 1. Now you can see where if this number wasn't a 1 in the front, if it was a 2, now that just doubled everything. If it was a 4, factors of 4 are 1, 4, and 2, and 2. So you have 1, 4, 2. It's going to triple all your work. Okay? So in the old school days, you would have this list of numbers to guess and check from. And eventually you'd get good at guessing and checking. You figure out patterns and things to look for. But we also have a graphing calculator. So you can type this into the graphing calculator, see where it crosses. So we have x to the 4th minus x to the 3rd plus x squared minus 3x minus 6. Looks like we're going to be checking out -1 and +2. -1 and +2. So we can start with +2, 1, -1, 1, -3, -6. Do our synthetic division. All right, 2 did work, just like we thought it should. And we're going to go with -1. And that one worked as well. And you're left with x squared plus 0x plus 3. This one's just the rational zeros. So there we are. Our rational zeros are 2 and -1. Like we talked about before, if the leading coefficient is not a 1, then your possible rational zeros goes up pretty quickly. We can use our graphing calculator to speed up the process like we just did. Okay, and we can use our graphing calculator to come up with values to use for synthetic division. And then that makes our life a lot easier. If you're just looking for the rational zeros. All right. 2x to the 4th minus 9x to the 3rd minus 18x squared plus 71x minus 30. Why don't you try to find the rational zeros? And this would be not very much fun to go through and do the factor list of 30 divided by the factor list of 2. So why don't you just jump straight into the graphing calculator part to find some nice numbers to do synthetic division with. Once you get down to the x squared level, I think it's just easier to do normal factoring techniques at that point. So give that a shot. All right. Welcome back. Let's see how we did. So what I chose, I saw that there was like 3 nice ones and 1 like decimal one that could have been a pretty nice decimal. We'll find out. So I just picked like left to right. So I just did -3 first. All right, so bring the 2 down. Negative times negative is a positive 45. -81, -10, positive 30, 0. And then I did the 2. Alright, so we have 2x squared minus 11x plus 5. And we can do our other factoring techniques. Maybe it's guess and check, maybe it's the magic X, maybe it's the box method, whatever you like to do. And I'm going to get 2x minus 1 and x minus 5 for answers of positive 1/2 and positive 5. So 1/2 is rational, right? Rational just means you can express it as a fraction, with most of these being over 1, negative 3 over 1, 2 over 1, 5 over 1, and then that one would then be 1/2. That's a fraction, 1 over 2. 5, find all real zeros. Okay, real zeros, so we're still not dealing with our imaginary friends yet. So we can use synthetic division, type into the calculator. Negative 2 looks like it works. We'll use 1, negative 7, negative 11, 14. Again, those are all coming off of the coefficients up there on the top. We'll have negative 2, add down negative 9, positive 18, 7, negative 14, 0. Okay, so just by the wording of it being find all real solutions, I'm kind of anticipating here a not very nice spot. Okay, I'm not thinking of anything that's going to multiply to 7 and add to negative 9 in the middle. Guess what that means? Quadratic formula. So negative b, negative of negative 9, plus or minus negative 9 squared, 4 times 1 times 7, all over 2 times 1. Negative b plus or minus, big square root, b squared minus 4 times a times c, all divided by 2 times 1. 53 on the inside, that does not reduce. And there's your other two zeros. 9 plus the square root of 53 over 2, 9 minus the square root of 53 over 2. Alright, we're getting into the fun parts. Imaginaries. Pairs of complex zeros of the form a plus bi and a minus bi are conjugates, and imaginary numbers happen in conjugate pairs. So if you get a plus bi, you also know that there's going to be a minus bi. Okay. So find a fourth degree polynomial function with zeros, negative 1 again, and 3i. Well, if you have positive 3i, you know you're going to have negative 3i. So negative 1 would be x plus 1, x plus 1, x minus 3i, x plus 3i. So we're going to have a big sloppy mess here for a little bit. X plus 1, maybe just break this up into pairs here, huh? And do this side first. And then on this side, this is going to come down x squared plus 3ix minus 3ix. Those would cancel. Minus 9i squared would be plus 9. So if you want to FOIL those out, you can. It should come out to x squared plus 9. All right, now we can multiply this out. It's kind of like FOILing, but it's not FOIL. There's not 4 things. There's going to be 6 things because you're doing a 3 times a 2. But it's still the same idea. This one to both of those. Then this one to both of those. And then this one to both. And we put all that together. Ta-da! X to the 4th plus 2x cubed plus 10x squared plus 18x plus 9. Linear factorization theorem shows that you can write any nth degree polynomial as the product of n linear factors. However, this result includes the possibility that some values are going to be complex numbers. Okay, the following theorem says that even if you do not want to get involved with complex factors, you can still write f of x as a product of linear and or quadratic factors, because these imaginary parts come from square roots of negative numbers, so you should be able to write these all as linear factors or a few quadratic factors on the side. And just don't reduce them all the way because to get your imaginary linear parts. Okay. A quadratic factor with no real zeros is said to be prime or irreducible over the reals. Be sure that you see this is not the same thing as being irreducible over the rationals. Example, the quadratic of x squared plus 1 could equal x minus I, x plus I is irreducible over the reals and therefore the rationals. On the other hand, the quadratic x squared minus 2 would factor out to x plus the square root of 2, x minus the square root of 2, is irreducible over rational numbers, but still reducible over real numbers. Those are still real. So if it's irreducible over the reals, it would not be reducible over the rationals either, because rationals are real numbers. If it's irreducible over the rationals, it does not necessarily mean it's irreducible over the reals, because rational numbers are not all the real numbers. But real numbers would include all the rational numbers. So think about that for a second. Okay, find all the zeros given that 1 plus 3i is a 0. Okay, so you got a couple options here. Option 1, and this is a bit of a longer one, is to, and we'll go through this one, if this is 1 plus 3i, if that's a root, then I know I have x minus 1 plus 3i, and I know I'm going to have x plus, nope, again, x minus 1 plus. I already used the plus. Let's say that again. So, all of our roots come in the form of x minus r, whatever you minus your root. So if 1 plus 3i is a root, we have x minus 1 plus 3i. Imaginaries happen in conjugate pairs, so I'm also going to have x minus 1 minus 3i. And that's the tricky part there, and I even stumbled over it, is that this part is always going to be the minus, and then in here, it changes. So when it's just like 3i, that's pretty easy. It's going to be x minus 3i, x plus 3i, and that would come from x minus 3i, and then this is x minus negative 3i. The sign still changes on the 3i, but it makes that be a plus. It gets complicated when you have these expressions. The minus actually changes in here, not in front. So then you'd have to distribute this. Okay, you can multiply this out, or you can take my word for it, that this comes out to be x squared minus 2x plus 10. And now they want you to do long division. Long division. I don't know why I did the square root sign. Long division with this whole thing. Okay, with this big long one up here. And you get x squared minus x minus 6. Hey, I can factor that pretty easy. X minus 3, x plus 2. Okay, the shorter way might have been to just jump right into the synthetic division with the nice ones from your calculator, 3 and negative 2. You get down to this, and now I'm going to do a quadratic formula for there, and I'll end up with x minus 3i, or 1 plus 3i and 1 minus 3i. Either way, they're both kind of long. They're both kind of long. Whether you're given this one and you do the conjugate, multiply them together, synthetic division, or long division, excuse me, and factor that. Or the other way is to look at your calculator first, get the nice ones, 3 and -2. Do the synthetic division first, get to here, quadratic formula, and now you'll get those. Either way, it's a long way. A lot of work. Right, this is a product of linear factors and list all its zeros. So type this into the calculator. We get one nice one. It's 3. So we're going to do synthetic division with 3. Okay. And now I have x squared minus 8x plus 17. And I have to do the quadratic formula from there. Negative of -8 is a positive 8. Negative 8 squared plus or minus 4 times 1 times 17 all over 2 times 1. So this is going to be 64 and this is going to be 68. So 64 minus 68 is -4. So we'll have 8 plus or minus the square root of -4 is going to be 2i over 2. Those are both divisible by 2, 4 plus or minus I. So we have nice numbers. We have a root of 3, and then we have 4 plus or minus I. And a story problem. Why not? You're creating a mold to make a pyramid-shaped resin trophy with a square base. So all the way back to geometry, we're thinking pyramids. You have 24 cubic inches of resin to pour into the mold, and you want the height of the trophy to be 5 inches more than the length of each side of the base. So it's a square base. Write a function that represents the volume, V, of the mold. So volume equals, let's think back to geometry, volume of a pyramid. 1/3 base area times height of the prism, or the pyramid in this case. 1/3 times the base area, well, it's a square, so x times x, and we wanted the height of the pyramid to be 5 inches more, so x plus 5. Alright, so you can leave it like that. Maybe you want to go 1/3 x squared times x plus 5. Okay, what should the dimensions of the trophy be? Alright, well, I know my volume is 72. 24. Skipped a step. 24 equals 1/3 x squared x plus 5. Okay, we're going to multiply that 1/3 over 72 now. Multiply both sides by 3. And we can multiply this through. X to the third plus 70. I keep wanting to get that 72 in there. X squared times x to the third plus 5x squared. Let's subtract that 72 over. And I'll let you type that into the calculator and see where it crosses. Where would it be 0? Is there a nice one that would work? And if so, what does that mean for the dimensions of your trophy? Alright guys, thanks for watching. Good luck on your homework, and let me know if you have any questions.